Leah here from LeahForSci.com, and in this video series, I'll teach you what you need to know about comparing acids and bases in organic chemistry, starting from understanding how pKa and Ka values relate to acid-base strength without doing calculations, followed by the factors you want to look at when comparing stronger to weaker acids, and finally we'll do some practice problems to determine which direction of equilibrium is favored in a reaction. You can find my entire series on acids and bases, along with the acid-base cheat sheet and acid-base practice quiz, by visiting my website, leahforsci.com/acid-base. Recall from general chemistry when studying acids and bases, you went through Ka and pKa values, Kb, pKb, ice charts, and lots of tedious math. In organic chemistry, you're likely not looking at any math when it comes to acids and bases. Instead, you're going to learn how to compare molecules by understanding them, by analyzing different components of the reaction to determine which one is stronger or weaker and which side the reaction will favor. No numbers, no charts, just pure logic. So the first question you have to ask yourself is, what is an acid and what is a base? In general chemistry, you learn 3 different definitions for the acids and bases, and these will still come up, so let's start with that. The first is the Arrhenius definition, which tells you that an acid is anything that donates an H+ in solution, specifically in an aqueous or water solution, and a base is anything that will give you an OH- in an aqueous solution. Examples include HCl. When I drop HCl in water, it breaks up to give me an H+ and Cl-. And for a base, NaOH. It dissolves to give me an Na+ and an OH-. The next definition is Bronsted-Lowry. And don't think of this as a new definition. Think of this as a more complete definition, because the Bronsted-Lowry acid is something that will donate an H+ in solution. So we'll call it an H+ donor, and that solution does not have to be water. So for example, if I take HCl and I dissolve it in ammonia, which is NH3, it'll still break up to give me H+ and Cl-, but because it's not in water, it's not an Arrhenius acid, but the fact that it still donates an H+ makes it a Bronsted-Lowry acid. Now, since we're not dealing with water, our base isn't necessarily OH-, but simply any ion or molecule that can accept an H+ in solution. So the Bronsted-Lowry base is something that accepts a proton or an H+. You'll hear me use proton or H+ interchangeably. I want to make sure you understand that they're the same exact thing. A hydrogen atom is something that has 1 proton and 1 electron. If we have deuterium, the isotope, then it has 1 proton, 1 neutron, and 1 electron. If I take that hydrogen atom and turn it into a cation or a positive ion, what I'm doing is removing that electron, removing that negative which balanced the positive, and that leaves me with an H+, which is simply a proton because there's nothing else there. So an H+ ion is a proton. Don't forget that. An example of a Bronsted-Lowry base, if we're looking at the ammonia solution, would be ammonia, because the ammonia will react with a hydrochloric acid and accept that proton to give you NH4+. The final definition is the Lewis acid and base, and this is different than the other two because we're not looking at the transfer of a proton between 2 molecules. Instead, we're looking at electrons. And the way I remember this is I think of Lewis having to do with electrons. A Lewis acid is something that accepts a lone pair of electron. Okay, E- is how I'm going to refer to electron, and PR for pair. And the Lewis base is something that donates the lone pair of electrons, so we'll call it an electron pair donor. A good example you'll see for a Lewis acid is AlCl3 or even BH3, which show up in your reactions. And the example for a base can be anything with a lone pair of electrons, for example Cl- or even a pi bond, as you'll see with your alkene addition reactions. So most students memorize the 3 definitions, and then they're faced with a reaction and they don't know where to go. Keep in mind, these definitions are not mutually exclusive. You can have a molecule fall into more than one category. The purpose of these 3 categories is simply to understand how to look at the acids and bases regardless of water, another solution, or even no proton being transferred. And I'm going to prove that to you with an example. We'll show what happens when OH minus reacts with H plus to give me a product in equilibrium that is H2O. You should recognize this as the reverse reaction of the autoionization of water. The reaction takes place as follows. OH minus will use one of its lone pair of electrons to reach out for and grab the red hydrogen. The electrons that reach for hydrogen now form a bond, and we have the molecule of water. Since water is the product, let's assume that this is taking place in water, making it an aqueous reaction. And we can also assume that OH minus came from NaOH and H plus came from HCl. According to the Arrhenius definition, the acid gives me an H plus in water, which we have. The base gives me an OH minus in water, which we have. So these classify as Arrhenius acid and base. The Bronsted-Lowry definition tells me that I have an H plus donor and H plus acceptor. Well, guess what? When OH minus attacks the H plus, it's accepting the proton, and the Cl minus that gave up that H plus donated a proton. So it falls under the Bronsted-Lowry category as well. And lastly, the Lewis definition has to do with electrons. Well, how does the OH minus reach out for and grab that H plus? It uses a lone pair of electrons, which means that OH minus is a Lewis base donating its electrons, and H plus is a Lewis acid because it's accepting electrons. Most likely you're going to look at the Arrhenius and Bronsted-Lowry more than Lewis in this topic of determining strengths, but I want you to understand that they can fall under more than one category. So now we know the definitions, and we also know they can be the same or different, which makes it even more confusing. What am I looking for in an acid or a base? This is where you really need to understand rather than go through this checklist in your mind every time, because the questions are going to take too long to solve this way. So let's take a look. If I have H plus coming off a molecule, that molecule is likely positive or partially positive because otherwise it would not give up an H plus. If I have the Arrhenius acid giving up an H plus and the Bronsted-Lowry giving up an H plus, the molecule, in order to be able to give up that H plus, must be positive or partially positive. HCl has a partially positive hydrogen. H2SO4, partially positive hydrogen. Alcohol, partially positive hydrogen. And then we look at the Lewis acid. If something is going to accept a lone pair of electrons, those electrons are negative or electronegative. And if opposites attract and like charges repel each other, you're not going to have a negative molecule accepting a lone pair of electrons. In other words, the Lewis acid must be positive or partially positive in order to accept a lone pair of electrons. So what you'll notice here is that the acid, regardless of the definition, is going to be positive or partially positive. Now let's look at the bases. The Arrhenius base is OH minus. OH minus is negative. The Bronsted-Lowry base accepts a proton. It's accepting something positive, which means it could be negative, like OH minus, or partially negative, like the lone pair of electrons in ammonia acting as a base. And finally, our Lewis base is donating a pair of electrons. In order to have that pair of electrons to give away, the atom or molecule must be negative or electronegative, otherwise it would not give away its electrons. So the trend for the bases is simply something that is negative or partially negative. So now when you're looking at two molecules and comparing them in a reaction and trying to figure out which is the acid or the base, unless you're specifically asked for the Arrhenius, Bronsted-Lowry, or Lewis acid or base, just look for the one that is more positive as your acid and the one that is more negative as your base, especially when comparing a molecule and its own conjugate, because an acid will become more negative as a conjugate base, and a base will become more positive as a conjugate acid. So we understand the definitions. Now we have to know how to determine what is an acid and what is a base. So if I give you a molecule, H2O, is that an acid or is that a base? Well, let's see. An acid would break up to give me H+, a base would give me OH-. Water can do both. So what you need to do is look at your molecule in context of the reaction or in comparison to another atom and see what you can come up with. I can show you water acting as both an acid and a base depending on which reaction I'm looking at. If water breaks up to give me an H+ and an OH-, then water is giving up a proton, making it an acid. On the other hand, if water is going to react with and accept a proton to give me H3O+, then water acts as a base because it's accepting a proton. Now this is the proper way to look at it, but in reactions you don't necessarily see the individual ions. You may see molecule A and B forming molecules C and D. So here's another way that I like to look at it. Compare the molecule that reacted. In this case we have an oxygen and an oxygen, so these two are conjugates. When an acid reacts, it forms a conjugate base because the molecule it forms is a base. When a base reacts, it forms a conjugate acid. Conjugate simply means the thing that formed at the other side of the reaction. And here we'll compare again the species containing oxygen. Here's what you want to look at when determining if it's an acid or a base. So as we said before, we're looking for the one that is more positive as the acid, more negative as the base. H2O versus OH-, we're comparing neutral to negative. The neutral is more positive than the negative, making it an acid, and OH- is more negative than something neutral, making it the conjugate base. For the second reaction, H2O, being neutral, is more negative than a positive H3O+, making this the base, and H3O+ is more positive than the neutral water, making it the conjugate acid. Now what if you're not given a reaction? What if you simply have two molecules and you see Ka or pKa values? Or what if you're not given any values and you're asked to compare them? That's exactly what we'll discuss in the next video, which you can find on my website along with the acid-base cheat sheet and acid-base practice quiz, leah4sci.com/acidbase. Are you struggling with organic chemistry? Are you looking for resources and information to guide you through the course and help you succeed? If so, then I have a deal for you. A free copy of my ebook, 10 Secrets to Acing Organic Chemistry. Use the link below or visit orgosecrets.com to grab your free copy. After downloading your free copy of my ebook, you'll begin receiving my exclusive email updates with cheat sheets, reaction guides, study tips, and so much more. You'll also be the first to know when I have a new video or live review coming up. If you enjoyed this video, please click the thumbs up and share it with your organic chemistry friends and classmates. I will be uploading many videos over the course of the semester, so if you haven't subscribed to my channel yet, do so right now to be sure that you don't miss out.